Welcome everyone back. Sorry for the short break, but at least we got the technology fixed for the first talk. Our second talk this morning is by Francis Brown on extensions of mixed Hodge structures and completions of fundamental groups. Francis, the floor is yours.
Thank you very much. First of all, thank you very much for this invitation to speak. I was originally asked to give a survey lecture on motives and how to the problem of knowing when say mixed Hodge structures come from geometry. That's a little bit of a minefield and not my main domain of expertise. So I've decided to focus on something much more specific, which is the question of when extensions come from algebraic geometry. So here we take two pure mixed Hodge structures, two pure Hodge structures that we know come from geometry. We know the cohomology of a projective, smooth projective variety, for example, and we asked how do we construct extensions in nature, in geometry. So that's what I'm going to talk about. Again, this talk is kind of informal, and I realize I may have misjudged the level at which to pitch it. So I hope you'll forgive me if some of this insults your intelligence and your expertise. So please bear with me. So to set the scene, the general pictures we start with, say, a smooth algebraic variety over a field K, which admits an embedding in C, since we're doing Hodge theory. And to this, we can attach a load of cohomological invariants. The first is singular homology of the complex points of that variety, which is the smooth manifold. So that's given by the singular cochains. And that's just a vector space over the rationals of finite dimension. On the other hand, Grothendieck defined the algebraic Duram cohomology, which is now a vector space over K, again of finite dimension, and in fact of the same dimension. And this is defined to be the hypercohomology of the sheaf of Kähler differentials. And that comes with a Hodge filtration. And in addition, we have a comparison isomorphism, which is an isomorphism between the Duram cohomology tensor with C and the Betti cohomology tensor with C in that direction. In particular, they have the same rank. And the comparison is, of course, given by integrating differential forms over cycles, over chains. There's a whole bunch of other structures that we may or may not wish to think about. So Deligne showed many years ago, of course, as everybody knows, that there is, in addition to this structure, there is a weight filtration, which is natural and which is geometric. It is not like the Hodge filtration, which is something that is peculiar to the Duram theory. The weight filtration is geometric. So that means, in particular, that the Betti cohomology and the Duram cohomology have a weight filtration. And that weight filtration is compatible with the comparison isomorphism. It's respected by the comparison. And so what we can do is to look at the Betti cohomology with the induced weight filtration and the Hodge filtration transported from the Duram cohomology onto the complexification of Betti via the comparison. And that's naturally a Q mixed Hodge structure. So since this conference is about mixed Hodge structures, I'm going to talk about mixed Hodge structures. But in reality, I much prefer to work with something which contains more information. And in my mind, this is what I will have in my mind when I talk about some of the later constructions. I prefer to work in a category of realizations, which means you can consider the Betti cohomology, which is a vector space, the Duram cohomology with the vector space, and in addition, the data of the comparison, the weight and Hodge filtrations, and perhaps other data if you so desire it. So these categories were first introduced by Deligne. They're abelian tensor categories, in fact, Tannakian categories. And they are better because they contain more information. So when we do mixed Hodge structures, we lose the rational structure on Duram. And when you talk about periods, you need that, of course. But anyway, for today, let's talk about, I'm going to work with just mixed Hodge structures, bearing in mind that in my mind, I often have a slightly more enriched picture in mind. Okay. There are lots of variants. Of course, this sweeps under the rug the work of a vast number of people, and I apologize for that. We can look at relative cohomology, cohomology of X relative to for example, some normal crossing divisor D, for example. We can look at cohomology in families over some base. And now we gain a lot of additional structures such as Gauss-Manin connections on Duram cohomology, monodromy representations on Betti cohomology, and so on. We can also work with cohomology with coefficients. So for Betti cohomology, this would be cohomology with coefficients in a local system. In Duram, we take coefficients in an algebraic vector bundle with integrable connection, for example. So this is extremely rich. And in fact, to answer the question I want to raise today about extensions, we will need all of this. So the spirit of the question I was asked to talk about is the sort of following philosophical picture. We have some kind of category of motives, whatever that may be, defined in whatever manner is possible at this point in time. And then we'll have realization functors, plural, which will assign to that some linear algebra data. And it's up to us to choose which linear algebra data we want, many variants. And the questions are, when does some given linear algebra data actually come from algebraic geometry? And a related question is when is this realization functor fully faithful? And it had better be, otherwise we're in a lot of trouble when we talk about motives. Good, so that's what I'm not going to talk about, but I'm going to, so, oh yeah, what I meant to say was that in this context, you have the Hodge conjecture, the Tate conjecture, and the Grothendieck period conjecture, and they're not at all equivalent. There's a very complicated, many variants and many interrelations between them, and that's precisely why I didn't want to talk about them. But what I am going to talk about is something very specific. So to introduce it, let me briefly talk about the Tate objects, which I'm sure everybody knows very well. And let's just take X to be GM, multiplicative group. Then its Duram cohomology is one-dimensional. It's a one-dimensional Q vector space, so I'm working over Q here, spanned by the differential form dx over X. The Betti cohomology is the dual of a class of a simple loop around the origin. Again, it's rank 1. And the comparison map is given by integrating this form over this cycle, so it sends 1 to 2 pi I. And the associated mixed Hodge structure is called Q of -1. It has Q of weight 2, type 1, 1. Though, as I said, in my mind, when I think of Q of -1, I really also want to carry a lot of additional structure as well, but I won't talk about that. Okay, so when we have the usual notation for Tate twists, M minus N, it is the tensor product of M with N copies of Q of -1. Okay, good. So what's the question? So the question is, given the cohomology of a smooth projective variety over Q, or a summand thereof, so I want to take a pure Hodge structure, which we know comes from algebraic geometry. We want to ask the question, how do you find extensions of mixed Hodge structures, or some refined notion, in geometry? So it's an extension of M with some arbitrary Tate twist minus N by Q. And so the input data is, if you like, the variety X, and we need to cook up some algebraic varieties in which we hope to find such an extension of mixed Hodge structures. Now, this is an important question because the existence of such extensions was predicted by Beilinson's conjecture. So the number of the dimension, so the rank of the X group can be predicted by Carlson's formula, or the variant of Carlson's formula. So there's a formula in terms of the Hodge and weight filtration and the action of complex conjugation on the Hodge structure of M. It's related to the L function of X, which is very interesting because it's got nothing to do with Hodge theory. The L function is defined in terms of Untitled homology. It's an arithmetic object. This question of the X groups is related to motivic cohomology and very closely related to algebraic K theory. And it dictates the structure of categories of motives. So what I mean by this is we expect that the category of motives over a point should not have higher X groups. So if you know the simple building blocks and you know the extensions, then you know the structure of the category. Of course, you don't know the objects in the category. That's a different question, but you know something about the structure of the category. So this question of extensions is very important. So the first example is very basic. Let's just look at an extension of Q of minus 1 by Q, right? And here the answer is really easy. We can write it down. Let's take X, a point in our field that's not equal to 0 or 1, and we can write down a Kummer motive. So here we see relative cohomology appearing for very good reasons. We take the first cohomology group of GM relative to the 2 points 1 and X. And the long exact sequence for relative cohomology shows that we have Kx is an extension of the H1 of GM, which we saw earlier was Q of minus 1, by the reduced cohomology of a pair of points. That's just Q. And so we've constructed a whole bunch of such extensions very easily. Now the periods of this rank 2 object, this extension, are log x, because that's just the integral of dz over z along a path from 1 to x. Now the conjecture is that whenever you have this situation in algebraic geometry, which happens a lot because you can cut out using the weight filtration such extensions very frequently out of the cohomology of algebraic varieties. Whenever that happens, it should be equivalent via correspondences to such a Kummer extension. And that, I believe, is a completely open problem. Now here in this example is too simple. It's misleading because these extensions fit into a family. We can allow X to vary, and we get a family of variations, and they're all simple extensions of this type. In general, that's absolutely not going to be possible. For example, in the next case, it won't be possible. So the next example is an extension of Q of minus n, now with a bigger Tate twist, by Q. And these are much, much more difficult to construct. So already over the number field Q, we sort of expect, I guess it's a conjecture in some sense, in a precise context, it's a theorem, that any such extension should always split when the Tate twist is even. When it is odd, there should be exactly one such class of extensions, and the period should be the odd zeta value, zeta of 2m plus 1. So of course, as I said, there are circumstances in which this is true, but in full generality, without any conditions on where we're working, that this is conjectural. So I've written Apéry here in brackets because, in fact, this is quite tricky. And I wrote a little paper a while back in which I interpreted Apéry's proof of the irrationality of zeta 3 as precisely giving a geometric construction of a family of extensions of this nature when n equals 3. And in fact, you can show that a big part of irrationality proofs come from precisely this problem. So it's not at all trivial. Over a general number field, this is very complicated to construct these extensions. They are related to the Dedekind zeta, the values of the Dedekind zeta function, if you look at all such extensions. But if you pick any particular such extension over a number field, the periods are not known. There is no recipe from Untitled homology that will predict the periods. That's unknown. Now, my understanding is that some work of Girdis many years ago in his PhD, so I think he unfortunately left mathematics, but I think a consequence of his thesis is that you can construct all such extension over number fields geometrically using hyperplane arrangements. And in fact, if K is totally real, you can do it using arithmetic groups. So that's something I did as a sort of a side project during my PhD thesis. It's a paper in Invenciones. the general case of general number fields via this method is difficult. So all that to say that this is a tricky problem. Now, the main example I'm motivated by is not extensions of rank 1 objects, Tate objects, but things related to modular forms. So let's take X gamma, a modular curve with E, the universal elliptic curve over it, and we want to take a summand of the cohomology of a modular curve with coefficients in the mth symmetric power of the H1 of the universal elliptic curve. So typically M will be cut out by Hecker operators. We might need to extend scalars to do that. M will be a rank 2, or be a direct sum. Well, yeah, if we extend scalars, we can take M associated to a Hecker eigenspace, in which case it'll be rank 2 when it comes from a cusp form, and its Hodge numbers will be 0, M plus 1, and M plus 1, 0. So then we can ask, how do we construct extensions of Tate twists of this rank 2 Hodge structure by Q? And it is related to, by Beilinson's conjecture, it's related to values of the L functions of modular forms. And the reason why I will introduce some of the later objects in this talk is that, in fact, you can answer this problem using some of the constructions that I will introduce later on. So this problem has a uniform solution. Right, so how am I doing? Fine. So what is the idea for constructing extensions? Well, one way to say it is the following, is that instead of looking at cohomology of X, our original variety, or varieties related to X, one should look at the fundamental group of X, or something related to the fundamental group. So this is the passage from the abelian world to the non-abelian world. So another more concrete way of saying essentially the same idea is the following. So instead of working with the cohomology of X, what we want to do is look at variations of Hodge structures or mixed Hodge structures on X. So here, I mean, I've written S here, but S will typically be X itself. So we'll take our variety X, and we want to construct lots and lots of extensions of mixed Hodge structure on it. And it turns out that that's much easier to do because of these these various theories of fundamental groups. And then what we'll do is then specialize to a point, and we'll just get a mixed Hodge structure. So that gives us a way to construct lots of mixed Hodge structures. Now, what I said earlier is a problem. There's a big problem here, and that's that extensions, or simple extensions of the type I mentioned, just never, almost never extend into families. The Kummer extension did, but this is never going to happen. So what one has to do instead is construct variations which are much more complicated. So they won't be simple extensions, they'll be iterated extensions. And when you take the fiber at certain points, they will collapse down to something much simpler. And that's when you're going to see the simple extensions appearing. Okay, so the idea is twofold. First, to pass to variations of a more complicated nature, and then specialize to a point at which they will simplify. So I'd like to illustrate this mechanism in action in the case of my second example. So we were on GM, and so we have the Kummer variation I mentioned earlier. Kummer variation, what K, was an extension of Q of -1 by Q. So here I want to regard Q of -1 and Q as constant variations on GM. And the Kummer, I remind you, in case you've forgotten it, oopsie, it is defined here. Maybe I can highlight, oh, fantastic. K of X, well, its fibers, oops, its fibers are the relative cohomology of GM to 2 points. It's very easy to construct this extension. You just look at GM cross GM relative to a diagonal and a horizontal line, and you take R pi 1 lower star, and that will give you this sheaf. Okay. Now, at the point x equals 1, so it extends at the point x equals 1, and the fiber at the point x equals 1 actually splits. And the reason for that is because the logarithm of 1 vanishes. And so, if you like, the period in the top right-hand corner of the period matrix, which gives the extension data, vanishes, and this is split. So the Kummer variation splits at 1, and in fact, it splits at any root of unity. So we could also take roots of unity in this story. So it is possible to construct polylogarithm variations, which are associated to the classical polylogarithm function here, which I've highlighted. So this is a very ancient functions defined by this formal power, defined by this Taylor series, which converges for absolute value of z less than 1, and they extend to multi-valued functions on p1 minus 0, 1, and infinity. So they have monodromy around 0 and 1. And so this is all the rage. At the time of the Motives conference, there were lots and lots of talks about polylogarithm variations. I won't give the definition, but it will pop out from something I'll mention later on. So what these are, they're certain variations of mixed Hodge structure on P1 minus 3 points that you can write down explicitly. And they're complicated. They're extensions of symmetric powers of these Kummer variations by Q. So these are the ones that you can write down easily, but they're much more, they're not simple extensions. They're much more complicated. They're extensions of extensions. They're quite tricky. But so this is what we can construct lots of complicated variations on P1 minus 3 points, and I'll explain exactly how to do that. But it doesn't answer our question. But the magic is that when we take the fiber at the point x equals 1, this Kummer variation splits, as I mentioned, and it becomes a direct sum. So the fiber at the point 1, you get an extension of the symmetric power of a direct sum, and that's just a direct sum of Tate objects like this with different twists. So there you get your a whole bunch of extensions, in fact. It turns out that most of them are trivial, except potentially the top one. So out of this, by doing a little bit of very trivial homological algebra, we can extract the extension of Q of minus n by Q, which I'll call E. So that's the highest weight 1 extension. And so we've got a potential extension of Q of minus n by Q. And now to check it's non-trivial, we need to compute a period. And that just turns out to be the value at 1 of this polylogarithm function, which is a value of the Riemann zeta function. Now, when n is odd, the value of the Riemann zeta function is not imaginary. So it is not a multiple of 2 pi I to the power of n. And that implies that this extension is non-trivial for odd n. So that explains how to construct the extensions in example 2 in a sort of systematic way. And there are several ingredients. The first is to construct this more complicated variation, the polylogarithm variation. The second step is to do some homological algebra. Well, sorry, the second step is to take a fiber and then do some homological algebra to extract from it some simple extension. In this case, that's trivial, but in general, I know of no way of understanding that problem without using some Tannakian machine. So that's the second step. And the third step is to check your extensions are non-trivial, and that requires some analysis. You've got to calculate some period. So I will not talk about the second or third steps in this talk. I will only talk about the first step. which is how to construct lots and lots of variations of this kind. Okay, so in this direction, there are a couple of programs. The first is due to Deligne many years ago. So the ideas I've mentioned are not at all original. So he considered unipotent completion of the fundamental group. Oh, sorry, I skipped a bit. I apologize. So I said I'd focus on the first aspect of the problem, and the first aspect was to construct lots of variations. And it turns out that's an easy problem because that is related to the fundamental group. We can use the theory of the fundamental group to generate lots and lots of extensions without too much obstruction. So we'll consider different notions of fundamental group. And the first of which is the unipotent completion. So this is part of Deligne's program to study unipotent completion of fundamental groups on quite specific spaces, namely P1 minus 0 roots of unity, nth roots of unity, and infinity. And of course, there's his very famous paper in which he first considered P1 minus 0, 1, and infinity, and more recent work in which he considered roots of unity, which are very interesting. So out of this, you can construct lots of extensions of Tate objects and much more, lots of iterated extensions. It's extremely interesting arithmetically. In a different direction, something that I've been interested in recent years and Dick Hain has worked a lot on is to study not punctured projective line, but a modular curve. So this could be a quotient of the upper half plane by, in fact, any finite index subgroup of SL2Z. So in general, this could be an orbifold. That's not a problem. It doesn't have to be a congruent subgroup either. You can take any finite index subgroup, and this theory works. Now, the problem with this is if you consider unipotent completion, you get nothing, because the unipotent completion of any of these groups is trivial. So you need to invent something new, and that's relative completion, which I'll talk about. And this construction, which is very much in its infancy, in fact gives a uniform constructions of the modular extensions I mentioned in my third example. And in fact, it gives a lot more. It gives extensions involving symmetric powers of motives, of Co Homology of modular forms, and so on and so forth. And it's of a lot of arithmetic interest. It's a lot of open, Beilison's conjectures open for many of these, in many of these cases. Okay, that brings me to completions of Pi1. So what's the general, so I thought I was ahead, now I'm behind, so I'll speed up a bit. Completions of Pyron. So what's the general picture? We're going to take a topological space, which is sufficiently nice that we have a theory of the fundamental group. And Pi1 x, y will denote the homotopy classes of paths from point x to y. And the homotopies have to respect the endpoints. And what the very general picture is we're going to replace this fundamental group. Well, this is a groupoid if we have different points, x and y. We're going to replace it with some schemes, something with much more structure. So for every pair of points x, y, you want to define an affine scheme, pxy, over q. And it mimics many of the properties of the fundamental path torso, homotopy class of paths. So I keep saying fundamental group, but of course it's not a group when you have x not equal to y, but I'll say groupoid from now on. So you get a groupoid, and the composition of paths is reflected by these schemes P. So if you have paths from x to y, you can compose them with paths from y to z and get paths from x to z. And so that reflects itself as a morphism of schemes between these different objects. And in particular, when where you're just looking at loops, x equals y, you get an actual group scheme. So this will define a group multiplication, and pxx is an affine group scheme. So how is it related to the fundamental groupoid? Well, there are natural maps from homotopy classes of paths into the rational points of these schemes, and they are Zariski dense. So think of pxy as some sort of algebraic hull of the classical fundamental group or groupoid. Of course, this map here can have a kernel. That happens a lot. And these maps are compatible with compositions of paths. Okay, so a very basic example to bear in mind might be, say, GM, the fundamental group of GM into Z, and we had the Co variation earlier, which is rank 2, defines a rank 2 local system, upon which the monodromy acts via these 2x2 matrices. And so the group Z sits inside this group of 2x2 matrices, and we think of the 2x2 matrices as a scheme. It's just its points are A, B, C, D, entries of a 2x2 matrix where D vanishes and A and C equal to 1. That's an algebraic group, of course. So Z maps into the Q points of this algebraic group. So that's a very, very silly example, but it's really the right intuition for the very general picture where we're going to take some algebraic Hull of Pyron. Okay, so, and then the point is that if we have a smooth algebraic variety over Q, say, then the affine ring, oh, sorry, this should read P, I apologize, not Pyron. The affine ring of P of X, X, Y, which is this scheme we're going to define, will, it turns out, have a Q-mixed Hodge structure. And so what we want to do is, what we'll expect to find is lots of interesting extensions sitting inside it once we choose our base points carefully. And that, as I mentioned before, that requires quite a bit of machinery to extract those extensions, about which I won't say anything. So how do we define P of X, Y? There's a sort of simple recipe to cook up as many notions of completions of fundamental groups as you like. And that's using the classical equivalence of categories between local systems and representations of the fundamental group. So the category of local systems of Q vector spaces on X, on the complex points of X, on X of C, what I meant to write. There's an equivalence of categories with the representations of the fundamental group given by taking the fiber at a point. So of course, if you take the fiber of a local system, monodromy acts. And conversely, if you have a representation of the fundamental group, you can push out along the torsor of paths, points from X to Y, to define your local system everywhere. So that's an equivalence. Now, one of our sort of one of the properties of this object P, which is some kind of yet to be defined completion of the fundamental group, is that it had a map from the fundamental group into its Q points. And so that tells us how we're going to have to define it, because what will be the representations of this group scheme? Well, the category of representations of this group scheme. So this is representations in the category of algebraic groups, okay? So if we take such a representation of the group scheme, so that's a co-module over the affine ring of P of X. If you take its Q points, that will, by this map, give you a representation of the fundamental group. And that's the same thing as a local system. So representations of our completed fundamental group will always give back local systems. And that means that they are local systems together with extra structure. And that tells us how to define them, because we should, that tells us precisely how to go about defining such a algebraic completion of the fundamental group. So here's the strategy. We consider any category of local systems, so this will be a full subcategory of the category of local systems. We want it to be an abelian tensor category, more technically a Tannakian category, and we can define P of X to be the affine group scheme, which is the automorphisms, the tensor automorphisms of the functor omega X, which is fiber at X. And more similarly, we can define the sort of torsor of paths from X to Y to be the isomorphisms of fiber functors from omega X to omega Y. Now and by the main theorem of Tannakian theory, we will, from this group scheme Px, we can recover our original category from its representations. It is equivalent, the category we start with is equivalent to the representations of this group scheme. Now, there are many variants of this construction. If you want to do the Duram theory, we can consider categories not of local systems, but of algebraic vector bundles with integrable connections. We can put weight filtrations on them. We can put all sorts of extra data on our objects. And provided that they form a Tannakian category, we can then define P of X, some group scheme, to be the automorphisms of the fiber functor. And that gives a very general way to cook up all sorts of different notions of fundamental group. Of course, this is historically completely inaccurate. The first example is unipotent completion, which goes back to Maltsev and was studied by Chen and many, many others. And in this framework, it can be set up as follows. Our input category is just the category of local systems which are unipotent. So that means that they are equipped with a filtration of sublocal systems, V0 up to Vn, such that each successive quotient is a constant local system. And that means by the dictionary between local systems and representations of pi1, that the representation of pi1 will be by upper triangular or block upper triangular matrices in a suitable basis adapted to this filtration. So it's representations of pi1 that are upper triangular, like in the baby example I showed for GM with the upper triangular 2x2 matrix. So the unipotent completion is defined to be the automorphisms of the functor fiber at a point X of this category. It satisfies a very nice universal property, which I will skip. And there's a very explicit construction, which of course predates all the categorical stuff. This is my ordering of events is totally anachronistic. So here's the construction, which I think is due to Quillen. Experts may correct me if that's not completely fair. So what you do is you take the group ring over Q generated by the fundamental group. That's non-abelian, of course. And inside the group ring, there is the augmentation ideal. So the augmentation ideal is defined to be the kernel of the map, which from the group ring of pi1 goes to Q, and it sends any loop, which I can't highlight, oops, any loop goes to 1. So in other words, it's the ideal generated by gamma minus 1 for all loops gamma. Okay, so what we can do then is take the quotient of this group ring by n plus 1th powers of the augmentation ideal. So that those quotients form a projective system, but you can dualize them, and the duals therefore form an inductive system. And the limit of this inductive system, a priori of just vector spaces, is the affine ring of this unipotent completion. In other words, the unipotent completion is just the spec of this this inductive limit on the right. So you need to check a lot here. You need to check it's a commutative ring. You need to check it's a Hopf algebra. And so it's in fact a commutative connected Hopf algebra. And so its spectrum is an affine group scheme. Now there's a variant where you take paths from X to Y. That's very, very similar construction. You use the fact that you don't take the group ring, it won't have a multiplicative structure anymore, but you take Q brackets pi1 x little x comma little y, and that's a rank 1 module over this thing, and you can do the same construction. Okay, so Morgan and Hain showed that if X is a smooth complex algebraic variety, then this, the affine ring of the unipotent completion of the fundamental group has a natural mixed Hodge structure. And that's great because it means that it constructs for us many, lots of interesting extensions potentially. Another point I didn't write down is that actually this thing is big. You could worry that in everything I'm going to say, you could worry seriously that these completions of fundamental groups are just tiny. They could be trivial, in which case this theory is not going to give anything. But in general, that's not the case. You can show, you can control their size very effectively, and they're extremely rich. So even in the simplest example of P1 minus 3 points, Deligne considered this in great detail. You can show that the affine ring of the unipotent completion is in fact a mixed Tate motive. So I was trying not to mention the word motive too much, but I did by accident. I apologize. It's a motive over K, so it's not just a mixed Hodge structure. It has a lot of additional structure. So if you to pick up a base point over a field, over a number field K, then you've constructed a very complicated mixed Tate motive, which is very interesting. Its associated weight graded is very concrete. So sort of conceptually, it's very easy to get the size and shape of this thing. Its associated weight graded is just the direct sum of all nth tensor powers of H1, the first cohomology group of X. H1 of X is pure. It's just 2 copies of Q of minus 1. It's a direct sum of 2 copies of Q of minus 1. And so this tensor power here, if you unpackage it, it's just a direct sum of Tate motives, Tate objects Q of minus n, and they're exactly 2 to the n in each degree n. So it's very big. It grows exponentially large, but all the data, all the interesting stuff is in the extension data between these different Tate motives, of course. And that's extremely intricate, and it contains in particular these polylogarithm variations I mentioned earlier. So there's some filtrations on this. If you quotient out by a certain filtration, which actually counts how many times one of the components of H1x occurs here, then you land on the polylogarithm variation on the nose pretty much. Now here's a construction that is unfortunately not very well known at all, even to experts in this subject, which is a shame because it completely answers a lot of the questions in the subject in a very effective way. And it's due to Beilinson, and it was never published. And this is probably why it's not so widely known. And Beilinson gives a direct geometric construction of this affine ring of unipotent completion in a very general case. And so it immediately implies a lot of the properties that it has. So let's just look at the case where x is not equal to y. And his construction is as follows. You consider n copy, you take the product of x with itself n times. And inside that, you have a very nice, very natural divisor, which has n plus 1 components. So the first component is sort of the vertical one with based at the point x. And the intermediate ones are just consecutive diagonals. And the final one, oh, I apologize, here's a typo. This should read y here. So it should be the horizontal one passing through the point y. So here's, to make this more clear, here's a picture in the case n equals 2. So we've got x cross x. And we've got 3 divisors. We've got the sort of vertical one passing through our point x. We've got the diagonal y1, and we've got the horizontal copy of x, so x cross y, which passes through the point y. And I've assumed here that x is not equal to y, so they will form a triangle. You can also consider the degenerate case when x equals y, and these will not be normal crossing in that case. And there's a way to deal with that by taking a small variation on this construction. which is in a paper of Deligne and Goncharov. But let's just look at the case x not equal to y. So we have this variety and we have this divisor, and Beilinson proves this absolutely stunning theorem, which is that the n plus 1th quotient, sorry, the quotient of the group ring by the n plus 1th quotient of the augmentation ideal is isomorphic to the relative homology of n products of x relative to this simplex. And so by dualizing it and taking the limit, that means that the affine ring of unipotent completion is just a limit of these very explicit cohomology groups. Of course, there's more to say here. You need to know, first of all, I need to specify what these maps are in this inductive limit. They're sort of face maps, inclusion into a face of the simplex which these divisors y form. You've got to worry that the composition of paths corresponds to some morphism of algebraic varieties. Actually, to my knowledge, that's not been done in the literature. It's not very difficult, but it's not been written anywhere that I know of. So there are a couple of things to check, but what you get is phenomenal, because everything we know about algebraic varieties immediately transfers to the unipotent fundamental group. So we get the existence of a mixed Hodge structure by general theorems immediately, and we get a lot more. We get an Ital realization. When you have a model, a good model, you have crystalline cohomology, you have p-adic Frobenius, so on and so forth. There's all this extra structure that we get for free out of this construction. So that's the picture. Good, so I've just got 10 minutes left. Now I want to talk about a different notion of completion, which is relative completion. And this was something introduced by Dick Hain and studied in a series of papers starting from 1998, I believe. Now, relative completion is actually the completely general case. I might say something about why that's the case later on. So it looks specific, but actually it's everything, as opposed to unipotent completion, where we're looking at very specific local systems or variations which are iterated extensions of trivial constant variations. So now what we do is, instead of iterated extensions of trivial variation, constant variations, we're going to specify some sort of some building blocks out of which we want to construct all possible iterated extensions. Okay, so that data for these building blocks will be given by R, a reductive group scheme over Q. And we give ourselves a representation of the fundamental group into the rational points of this group scheme. So the main example we have in mind is the case of a modular curve. And in that situation, this group scheme will just be SL2. Okay. And this monodromy representation will be the monodromy representation on H1 of the universal elliptic curve, on the fibers of the universal elliptic curve. Okay, so we give ourselves this data. It's a Zariski dense by assumption. And this gives a map in the opposite direction from representations of R. So this is the category of representations as in the sense of algebraic groups, okay? So the representations of algebraic groups. Taking their Q points gives you a representation of the fundamental group. And what this does, therefore, it will define a semi-simple category of local systems on X. So another, you can turn this around and say we start off with a particular nice family of local systems on our variety X, and they should be they should come from the representation of a reductive group, and they will form a semi-simple category. So, for example, variations of pure Hodge structure which are polarized will do the job. Okay, so now we consider a category C rel, comma rho, which will be the category of all local systems on X, equipped with a filtration, an increasing filtration, now with the property that the successive quotients are the basic building blocks of the type we want, namely they come from representations of this reductive group R. And on this category, we have a functor to vector spaces. Here I've taken Q, I have a Q, which is taking the fiber at a point X. And it turns out that this category is an abelian tensor category. It's a Tannakian category, and omega is a fiber functor. So we can define the relative fundamental group, relative completion of the fundamental group, to be the automorphisms of this fiber functor, and that's an affine group scheme. Okay, so that's the definition of relative completion. And the general property is that it is an extension of the original reductive group we started with, R, by some pro-unipotent group, some pro-unipotent algebraic group. Typically, it's very big, so this object is extremely rich. There is a natural map from the ordinary fundamental group into the rational points of this relative completion. And it lifts, via this quotient map to R, it lifts our initial map R, which was part of our defining data. Okay, so the main example here is the case of a modular curve. So H is the upper half plane. Gamma can be any subgroup of finite index. As I mentioned before, it doesn't matter that this is an orbifold in many interesting cases. It's not a problem. The map rho from gamma, the reductive group R is just SL2, the group of 2 by 2 matrices with determinant 1, and the map rho is the inclusion of gamma into the Q points of SL2. The category C is the category of iterated extensions of symmetric powers of the H1 elliptic curve. And of course, these are very important in the modular theory, but we're now looking at iterated extensions of those. So one way to say that is this is really the non-abelian theory of modular forms for gamma. So classical theory of modular forms, you look at sections of these sim and H, and here we're looking at more complicated things. Okay, so in 1998, Dick showed that the following theorem, that if you start off with a smooth complex algebraic variety and V, a polarized variation of Hodge structure on X, you define R to be the automorphisms of a fiber of this variation at a point X with respect to polarization. That's a reductive group. You might need to assume, but this is not a very stringent requirement at all, that the representation of the fundamental group in the Q points of this reductive group should be Zariski dense. And under those assumptions, then the affine ring of relative completion will have a natural mixed Hodge structure. So that's the generalization of the theorem in the unipotent case, the relative case. So in the last couple of minutes, I wanted to mention a possible geometric construction of relative completion. So this is something I haven't thought about for ages. I wrote a letter, I think, to Spencer Bloch and Masha Vlasenko a few years ago and forgot about it. So I dug it out for this conference. It's very, very sketchy, but I'm sure this idea works. And there's only really, it's all pretty obvious. There's only one point that needs to be made. And so the idea is just to copy Beilinson's construction and give it and do that in the relative setting. And the idea is really just to do Beilinson's construction, but with coefficients. So what we can do is, so I remind you, since I have a couple of minutes, just to recall the picture of Beilinson construction. So you're looking, in this case, at x cross x relative to this triangle. And the idea is that you want to put coefficients everywhere. You want to look at relative cohomology, the same geometric setup, but you're going to put coefficient systems everywhere. So on the ambient space x cross x, and also on each stratum. And that should come very close to constructing the relative completion. But there's a caveat here. The caveat here is that in Beilinson's case, you can realize the unipotent completion on the nose as the cohomology of this beautiful geometric picture. And I don't think that's possible in the relative case, or not in a simple way. The best you can do is try to generate the affine ring of the relative completion out of cohomology, because in general, you're going to get some complicated relations. So one shouldn't try to construct it on the nose. One should try to have a map from some geometric setting to it. And that's exactly what I propose. So here we go. So we take, we're going to copy Beilinson's construction, but now we give ourselves some coefficient systems. So I'm working in Betty for now, so let's just take local systems. But of course, we could work with algebraic vector bundles with integrable connections if you wanted to do the Duram theory, for example. So we take a bunch of local systems, A, B, and L1 up to Ln. And they are local systems that come from representations of this algebraic group, which was part of the defining data for relative completion. And we construct the exact same, we look at x to the n, as in Beilinson, and we construct the exact same simple x sitting inside it. And we define y subscript I to be the intersection, I-fold intersection of, well, to be each stratum, basically. And then we consider this local system, this external tensor product on x to the n, and then restrict it to each stratum, and then extend by 0. Okay, and so that gives you, in the standard way, a complex of sheaves on x to the n. So you've got this complex here of sheaves that comes from this data of L1 up to Ln. That's part of our input. And then what you do is you take, exactly the same way as Beilinson's construction, which is just the case of constant coefficient systems, you take the nth cohomology of x with coefficient in this complex of sheaves, and you need to stick the fiber of A. We had these other local systems, A and B. We stick the fiber of A and tensor on the left and the fiber of B tensor on the right. And I claim by the theory of matrix coefficients in Tannakian categories, you get a map into the affine ring of relative completion. And it turns out that, so you can show next that for x a smooth curve, that actually if you allow n to go to infinity and allow your local systems to range over the entire category of representations of R, then actually you generate the whole affine ring of relative completion. And that's some induction on what's called the co-radical filtration. It's not particularly challenging. And so I believe if one could find the time to write these things up, that would give another a geometric construction of the affine ring of relative completion, and show that these extensions that we can find inside it indeed come from geometry. So I'm on the dot at 4:45, so I'll stop here.
Thank you, Francis, for a very beautiful talk, and we have time for questions or comments.
Yeah, I have a question / comment. So in this construction, I guess it would be best if you could make, the local systems world coming from geometry. And
yes,
and somehow to make it totally motivic, somehow realize, you've moved a slide. If you move.
oh, sorry. Yeah, no, you're absolutely right. So here is just the sort of topological version. The first thing you want to do is construct the relative completion of pi1 as in the group theoretic sense, and so you just do local systems. But you're quite right. So what you want is you want in general, if you want to do it motivically, so to speak, you want these to be higher direct images of variety sitting above X. So you have some map Z to X, and you take R pi lower star of a constant sheaf on Z, of Q on Z, and push it down to X. Does that answer your question?
Yeah, I think so. If you scroll down a little further.
Oh, sorry, I wasn't quite. I can't see you, and I'm not quite sure to what you're.
Yeah, okay, that's good.
But yeah, so you start off with X, and you want to consider Z above X, maybe infinitely many such Zs. So in the modular case, you'll have like some Kugasato varieties, right? And you can take the local systems A and B and L1 up to Ln will be high direct images from these algebraic varieties, and so they will be motivic in whatever sense you desire.
Okay. Thank you.
There are other questions or comments? If not, I'd like to again thank Francis for a very nice talk, and our next talk will be in about an hour and 15 minutes at 1 o'clock East Coast time in the US. So thank all of you for tuning in, and hope to see you at the 1 o'clock talk.